So let's look at this best linear estimation a little more. Let me start with a couple of examples. You go to a doctor's office, right? Say the doctor puts the stethoscope here, he listens to it, and then sometimes you have seen he takes the stethoscope and puts it somewhere else, right? So this is one measurement. That's because here what he or she is getting is a noisy version of the, let's say, from the heart. But then, and it is unclear, so maybe he or she is trying to listen to a particular valve, but all sorts of other interferences are there. Now with years of experience, that's where you want to go to a established doctor, right? So just to make sure, he or she would put the stethoscope somewhere nearby, right? Not on your head, but somewhere nearby. So the whole idea is you want to get an approximate idea about the interference. So but this interference itself may be even, it's not going to be exactly the same interference you would see here. So this is a noisy version of this interference. Then he or she would, you have to put back the stethoscope back here to listen to this. Then he or she is going to use the years of experience to cancel out this. Remember, you yourselves will say, I smell gas, so you go to another room, smell something, then you come back, and within that short time you can differentiate. Right? I've done this in my house, right? So the whole idea is you want to know whether there is any funny signal here, or it is just a noise at both the places, right? So you could think of this as Y1, one data set, and this is, it's already here. You could think of this, so this is your body, right? Think of this as the other data set. So you want to put all the data set together, and we want to get so this may be your unknown in this case. So remember, our notations are a little different from what we used to. So X is hidden. This true signal is hidden. I want to use the same notation that I gave you. And so this is your data now, right? What you measure. And you want Y hat. So the question is, how do I come up with a linear estimator? So best linear estimator, okay? Now let me give you another motivational case. In oil exploration or wherever, you have all these people in Texas who go around with a stick or something, right? That's one way. Other one is once, for whatever reason, you analyze some geological samples and you have a hunch that there is oil here. Then to test it out, you drill holes, and then you essentially blast tiny dynamite so that shock waves are produced. Then then of course, it's a very complex phenomenon. From every layer of the earth, you are going to get returns, right? So you are going to get the return signal. But if there is oil, then that particular signal will have its characteristics and so on, right? So you are looking, so this is the oil characteristics, and it is contaminated with all sorts of noise. So just to get some reference, you go somewhere nearby and do the same experiment, and you know that this data is more or less all the disturbances and so on. So what is going to come out here is this noise, but maybe a contaminated version of this. So we want to cancel out this noise, or adaptive cancellation. In other words, we want to use the data itself to pick up the bad parts of the data. And that's what the doctor does also like this, right? So this is the bad signal which you want to subtract out or cancel out. So then you stack all this. So you don't want to process this separately and this separately. You want to put all the data, all the observations, stack it together, and then get a best estimate. And so this is the processing you are going to do. So H is like this. This is your H. We are trying to figure out Y is here, all the data points, right? And this will come out to be your estimator for X. So in this problem, so this is a model-based approach. For whatever reason, I have assumed that your data has this form. A simple linear model, very popular, and you can see why it is. Look at here, doctor's office, signal plus noise. Second observation, noise plus contaminated noise. But if you are moving the stethoscope nearby, this noise and this noise should be dependent, right? So you don't move it all the way to the foot or something so that it becomes completely indifferent. If this is like this, it's useless information, right? This data has nothing to do with this, what you are looking for, right? So if you want to cancel out this noise, you have to make some measurements which is nearby, and that's the sort of idea here also. You don't even know what is signal, what is noise here, but by going nearby, you could get a second guess on the interference, and then we want to use this data itself to cancel out, without even knowing what to cancel. That's why we call it adaptive techniques. So look, from here, common sense would say, if you knew, for sure you know that this noise, what you hear, what you get here is this noise, then of course you are saying, look, from y1 you subtract out y2, of course you get ax, right? But it's not that simple, because this is a stochastic process. This is also a complex phenomena going on. Remember, we learned earlier, if x and y have equal variance, what is the variance of x minus y? Anybody? X minus y. X and y are, let's say, equal variance. Let's say they are uncorrelated. What?
2 times the variance of...
Right, that's the problem. Just by subtracting, if you don't, subtracting 2 random variables, you are making the situation worse. You are actually increase the variance. So you can say, I'll take y1 minus y2 is cleaner version. So it's a little more complicated than that. So these are the type of problems we want to solve. So I stack this data, I stack the second and third data, more the merrier, right? At some point, as someone said, computation, etc., may be too much, and it may not make sense. So how do you solve this problem? And so this is your data, and this is what we are looking for. H is what we need to find out. So again, we can use the same strategy. Notice that it is quite possible that the unknown itself is a vector. In this case, it was simple. Unknown is a scalar quantity. So what I'm trying to say is, generally, A would be like this. A will be long and thin. That means what? Long means what? Lot of data points. Thin means the unknown itself is only fewer. Which situation is better? You want it to be fat and short or long and thin? Because if it is the other way, that means we have few data points and too many unknowns, right? That's a indeterminate situation, right? Too many unknowns and too few data points. So it is better to be in this situation. So again, we look at error here, but error is, remember, this is what you are looking for, x minus x hat, and x hat is here, so this is x minus hy. So I'll sort of take you through the matrix case, but remember, if this is a vector, this itself is a vector. So what do you mean by mean squared error here? Remember, this is a random quantity because everything you see here is random except this. So you could look at this as, so this is the norm of this, which is the same as if epsilon is a vector, a column vector like this, then epsilon star epsilon will be a scalar, right? because epsilon star is the other way. Epsilon star goes like this. So that this is the same as sigma xi squared, expected value here. So expected value here. So this is one way to go. There are other norms we could use, but let me deal with the. So again, this is minimization of the mean squared error. Minimization need to be done. We need to figure out what is the best h to use here. So let me call this quantity to be sigma naught squared. Now, we could also, if you write the other way, so this is, if you write the other way, we can write this in terms of the trace also. So, where is epsilon? So you can also write this as the trace of expected value of epsilon star. What is trace? If you look at here, trace of a matrix is what? Anybody? Trace means what? Anyone? So if a matrix is like this is a, what is trace? Right, some of these elements, A11, A22, etc. So this is sigma I equal to 1 through n. Look at here. This is a scalar, right? Because epsilon star is like this, epsilon is like this. If you write the other way, epsilon is like this, epsilon star is like this. And if you create a matrix, you will see that the diagonal entries are epsilon 1 squared, epsilon 2 squared, etc., epsilon n squared. This is another epsilon I, epsilon j, everything expected value, right? So you see, you add up this, that's the same as this. So you could write it like that because it will help us with the simplification. So let me take this term. So this is a trace of epsilon star. So an identity in matrix is that this is very easy to check it. You can do it yourself. A trace of AB is the same as what? Anybody? You're just guessing, or? That's a good guess. Trace of BA. Look at here. So if you, so BA is, this is AB. BA will be epsilon star, which is what I have written here, right? Let me substitute for epsilon. Epsilon is here, look at here. So I'm going to substitute now trace of, trace means it is a scalar, right? Because I'm only adding the diagonal entries. So epsilon is x minus hy. Remember, everything is a vector. X star minus y star h star, right? You know why I changed y star h star? Because the complex conjugate of AB is AB star is B star A star, right? And there is an expected value. Trace is a linear operation, so there is an expected value. So there are 4 terms. Look at here. What is the first term? Expected value of xx star, right? Minus h expected value of hy x star minus right? Remember what x is. X itself is data set. Where is x? X itself could be like this, right? So x may be a stochastic process or whatever. sampled at several points. Y may be more data, but X is what we are trying to find out. So I'm going to call this is the autocorrelation matrix of X, right? This is the autocorrelation matrix of Y, the data set. So I'm going to call, usual notation, I'm going to call this RXX. I'm going to call this RYY. If Y is larger, this will be a bigger matrix. If this is smaller, if the size is smaller, whatever is the size of this, look, this is M by 1, 1 by M, so this will be M by M. Here you may have more data, so this is N by 1, 1 by N, so this may be N by N. All the sizes will work out. So you have H, H star. So let me write all the 4 terms. So this is a trace of RXX minus H. So let me also put a notation for this. So I'm going to call this matrix to be RXY. So this will be what? The conjugate of that, right? So this is RXY star minus RXY H star plus. Why this is plus is because minus minus twice, right? So let me so let's look at, so maybe you have not seen this r to the power half and so on. So look, if A is 4, what is A to the power half? Anybody? 2, right? So same thing you can do for positive definite matrices. Or to the, so the quickest way is if let me just state, if a matrix is positive definite, that also means the matrix can be written as this way. So how you do it, you can get the idea, right? How you do it is a different issue, but take it from me that that's possible. Then A, of course, is the notation is, you can see A is the square root, or generally we write it like this. Then A inverse is what we mean by r to the power minus half. Okay. So how to find out A is a different issue. If you know eigenvalues and eigenvectors, it's easy. So this should motivate you to go and read something and figure out. This is the way you learn also, right? So this is the square root. How do you find the square root of a positive? So it's not like taking a square root, because it's a matrix is like this. It could have negative entries, right? So in any case, that's what I mean by the negative square root and the, not negative square root, the inverse of the square root and the square root of the positive matrix. Why am I doing this? You will see this. What do I mean? What do I mean by, any questions? So this is something like this. So this is, of course, this means so let me write, so if this whole thing is Z, that's what I mean by norm squared is a trace of RXY RXY RYY minus half minus H. You don't have to write it down because I gave you the notes. And let me try the by the conjugate, see here, complex conjugate of that. When I multiply by the complex conjugate, remember R already has the property that R is R star. So its complex conjugate So this will come on this side, right? So this will be RYY minus half RXY star minus the other way RYY half H star. Now I need to multiply the whole thing together. So this is going to be trace of, look at here. So I have RXY, RYY inverse, right? RXY star, right? This multiplied by this will give me minus half plus minus half is half. Then this multiple, look at here, this will cancel with this. That's the whole point. Here you have RYY, RYY, plus and minus. So you get RXY, RXY, H star. And look here, this here and this two will cancel. So I get H RXY star. And the last term is minus minus plus. You get RYY H star. So now you can see, look at here, these three terms are there. See, this are the same as this. So these three terms are this minus this, right? So I'm going to replace these three terms with trace of Rxx, which is here. So that is going to be this minus this. So there is going to be a minus sign here. So this is Rxy star. We are almost at the end. R inverse Rxy. Then you have plus this minus this. So this is going to be here. Rxy, Ryy minus half minus H RYY half. Now you may be thinking, why am I doing all this? And you will see otherwise, look at the problem here. You want to minimize this with respect to what? What is the variable here? Unknown. What is unknown here? H itself is a matrix. It's not a scalar. Otherwise, I would do the derivative with respect to. You can do it with the term by term, etc. So I'm trying to find out the best H. So in any case, there's nothing wrong with this. This is true. This is true as an identity. If anybody thinks, so there is no issue. But look at here. I cleaned it there is no H here. So this is a constant. H is only here. Look at the argument now. You want to minimize this whole quantity. The whole point is to minimize this on H. Look, this is a positive quantity involving H. So the best value for positive quantity is what? If I minimize this, what is the best value I can hope for? Huh? 0, not negative, because it's a positive quantity, right? Look at here. This is the norm. So the best value for, the minimum value for this is 0. So when I can push this to 0, if I choose H carefully. H is going to be what? Push this term here. So you can see the H is going to be Rxy, Ryy inverse is the best H. Because you equate this equal to this. That means this goes and comes here. So this is a very classic solution. This will come up again and again. So you need the cross correlation between the data and the unknown, and data and the unknown, and you need the autocorrelation of the data. Remember, Y is the data. So let me write down the result. You don't need it. This was only an intermediate step. So I'll quickly do 2 simple cases and then we will stop this. So the best estimator is H is Rxy, Ryy inverse. So let's do example 1. Let's say y is this is everything is scalar. I just have one observation, right? So look at here. So I want x hat is h y, right? Because h is scalar, right? So h is rxy. So let's find out rxy. So this is of course rxy ryy inverse. Y is here. What is ryy? Anybody? Let's say everything is 0 mean. So ryy means what? Expected value of y squared, right? So that's going to be ax plus n squared. When you expand, how many terms are there? What is this? Anybody? I'm going to assume that the signal and noise are uncorrelated. A reasonable assumption. So this term is 0. This is, I'm going to assume this is the signal variance. This is the noise variance. So ryy is a squared sigma s squared plus sigma n squared. Okay. What is rxy? Anybody? Look at here. You can do it directly. What is rxy? Rxy is expected value of x multiplied by y, which is ax plus 1. Anyone? So that's 0, right? So what is it? A squared. So look at here. Let's apply for h. So h is rxy ryy inverse. That means a sigma x squared over a sigma x squared plus sigma m squared, right? So this is 1 over 1 plus so a is 1, let's say, right? If a is 1, that's that, or a is not 1, it is still 1 over. Sigma s squared over sigma n squared is signal to noise ratio, right? So what is the best estimate? If you only have, look at here, what it says is if you only have one observation, you just scale it. So the best estimator is 1 over some constant, 1 over SNR multiplied by A multiplied by the data. So the best thing the doctor can do is just listen to it and try to adjust the amplitude. There's nothing else to compare with. Let's do the same problem just to show you how powerful this method is. Let me bring in a second. So I'm going to call this the first observation. Okay. Hello. Any questions? So I bring in a second observation, y2 right? And I'm going to stack the observations together. So I'm going to be quick. So y is y1, y2, but y1 is given to be ax plus n. This is n plus w. So let's say a is 1 at this point. Okay. So let's redo the problem with a. Otherwise you just have to carry over a. So this is the optimum estimator. So this, if you want, you can write this as right. So this is your x, this is your a, this is your n. Right. So we need to find out again in this problem RYY, what, remember this is a 2 by 2 matrix, RYY is what? We can do it mentally here, look at here. The signal and RYY is, this the variance of this, right? Yes? This will be, I'm sorry, RY, this will be, there will be 4 entries here, right? The first entry is the variance of this. This is the variance of this. This will be the cross term. So let's do it mentally. The variance of this is sigma x squared plus sigma n squared. This will be sigma n squared plus sigma w squared. If you cross multiply this, what happens? X is uncorrelated with noise. X is uncorrelated with this. These two are uncorrelated. So there will be only one term, expected value of n squared, which is sigma n squared here. And let's find out Rxy also. So expected value of x multiplied by, so what do you get? X multiplied by y1. Look at here. Y1 is this. X multiplied by that is sigma x squared, right? And x multiplied by y2. Y2 is here.
0.
Right, 0. So we have Rxy. So all we need is Rxy is here. We need Ryy inverse. You should go home and check it. It's already there in the notes I gave you. So plus we are getting late. So let me just. Alright, so this is the right expression for Ryy, right? Page number 6 at the bottom. Ryy. This is the right expression. Okay. I mean it's computed differently, but bottom line. Now a 2 by 2 matrix, at least you can find the inverse, right? So that's done there. So you copy. So the inverse will turn out to be, if you want, I'll copy it here. I mean, after some simplifications. All right, so this will, then you just need to multiply to find out h. You need to multiply Rxy multiplied by Ryy inverse. So we have Rxy here, and this will turn out to be some constant multiplied by 1 minus sigma So this is the end. So this is a constant which is already there, and you have the notes in. So once you have h, remember x hat is going to be what? What was h hat? Hy, right? Right? Hy. So this is hy. So forget about the constant. This is only a scaling. So y is y1, y2. So what it says is this is. Look at what the optimum estimator says. Optimum estimator says you should, the best estimator is going to be from the first observation, take out a scale, the second observation and subtract it out. How much you scale with? Everything is adaptive. This is what we mean by adaptive estimation. The data itself tells you what to do. And that makes sense because you are trying to, see, your job is, look at here, your job is to get rid of this noise. If you only have one observation, the only thing you could do is scale it. You don't have anything. Look at here. Where was it? Here. So your estimator is going to be h multiplied by y1. So that's just y1 is scaled by nothing else. So this noise is not going to be, but nothing else you can do to this noise. You can, whereas with the second observation, you are able to subtract it out carefully. How much to subtract? The problem will tell you. It all depends on the variance of this, variance of the second noise, etc. Now, something I have not told you, which is there in the notes, is of course we expect that having more data should be better, right? So you could compute the mean squared error, which is, look at here, this is the mean squared error. We had this expression before, Rxx expected value of y squared minus gamma star R inverse gamma, remember? So you compute the mean squared, you compute this expression. So because this is equated to 0, so you just have this. You compute the minimum mean squared error on both the cases, and you can see that the second case, the error is lower.